Welcome back, everybody. So in this video, I'm going to hammer home some points about electric potential, some further discussion of electric potential, if you will, some points that I didn't mention in the last video, or maybe some points that I can show in a different perspective. And then what I'm going to do is calculate the electric potential around a point charge. And I hope it's a fun video. I hope it's not too long. Normally when I ramble away like this, it's like an hour. But we're going to start off here with electric potential searched up on Wikipedia. So here I have a screenshot. I'm just going to read it out from top to bottom. So electric potential, not to be confused with voltage. And down here we have a Wikipedia search on voltage, so we'll get to that in a second. But it says electric potential, also called electric field potential, potential drop, or the electrostatic potential, is defined as the amount of work/energy needed per unit of electric charge to move the charge from a reference point to a specific point in an electric field. So this little section right here, work/energy per unit charge to move a charge through some electric field is literally the definition that we had before. So the definition of electric potential, here I'm writing it as electric potential difference, but let's just remove that difference sign for a second. This little 3 equal sign thing is defined as, we have the electric potential energy per unit charge, and sometimes you'll see unit charge with a little O here, or a little knot. So this is how we've defined it. And why they say work/potential energy over here is because of this other equation where we had the change in potential energy equal to and opposite to the work done. And if you remember, the work was calculated as a force times some displacement. And once we plug in the Coulomb force, we get negative Q electric field dot product with the displacement vector. And then since we have this definition over here, electric potential energy per unit charge, we can get rid of this Q over here. So we define electric potential difference as the electric field dot product the displacement vector from some point A to B. So you can think about this as like the work it takes to move some kind of charge Q, the work it takes, or the potential energy it takes to move some charge Q through a potential difference or through some electric field like this. So I'm going to keep reading the Wikipedia article here to see if there's something more useful. More precisely, the electric potential is the energy per unit charge for a test charge that is so small that the disturbance of the field under consideration is negligible. The motion across the field is supposed to proceed with negligible acceleration so as to avoid the test charge acquiring kinetic energy or producing radiation. By definition, the electric potential at the reference point is 0 units. Typically, the reference point is Earth or a point at infinity, although any point can be used. Okay, cool. That last little section here, it gets a little bit more deep and brings in other forces like stuff like radiation, kinetic energy. Let's not worry about it too much. Just remember all these equations over here. And let's take a look at the voltage section. So I just clicked over here on voltage because it says not to be confused with voltage. They're saying electric potential and voltage are two different things. So let's see what voltage is. Voltage, also known as electric potential difference, electric pressure, or electric tension, is the difference in electric potential between 2 points. Interesting. So they say V, electric potential, is not equal to voltage, but the change in V, or electric potential difference, is equal to voltage. Okay, cool. And it also says it between 2 points. So this could be between point B and point A, for example. Or if you use the actual definition of potential difference, we have this negative integral electric field dot product with the displacement vector. This could be from point A to point B of the integral. In a static electric field, it corresponds to the work needed per unit charge to move a positive test charge from the first point to the second point. In the International System of Units, SI units, the derived unit for voltage is the volt. So this thing per unit charge has been stated multiple times. Here you have per unit charge, here you have per unit of electric charge. And one final thing I have here is just some points from ChatGPT. So I literally went into ChatGPT and I was like, give me a couple definitions of electric potential difference or electric potential. And we got a couple of points here. So one, scalar quantity. It says the electric potential is a scalar quantity that represents the amount of electric potential energy per unit charge. So here's the same definition said a third time. Electric potential energy per unit charge at a specific point in a electric field. It indicates the ability of the field to do work on a charge placed at that point. So I hope you guys seeing these same kind of definitions over and over again will kind of bring home the definition for you. The reason I'm doing this is because it's a weird thing, this V per work per charge or potential energy per charge. It's weird, but seeing the definition over and over, you'll kind of get the hang of what it is, and working with some of the equations, you also get the hang of what it is. So it's hard just explaining this concept in one clear sentence because it uses so many strange words in the definition itself. So let's take a look at the second one. It says work done by an electric field. This is actually a very nice definition. You can think about electric potential as the work done by an electric field. This is kind of the definition that we use most often in circuits because we use voltage as kind of the powerhouse of a circuit, like a battery, for example. So it says it can be defined as the work done by the electric field in moving a test charge from a reference point, often infinity, where potential is zero. This is going to come in handy when we calculate the potential energy around a point charge. So I would say just remember this. We'll get back to it in a second though. To a specific point, divided by the magnitude of the charge. Mathematically, they give you this equation here. This equation is pretty much the same thing as electric potential is electric potential energy divided by the charge. Or I'm writing an arrow over here, not an equal sign. They say work per charge. Where and then I'm gonna keep reading down here, where V is the electric potential, W is the work done, and Q is the charge. Now let's see one more final point, and then I'll get to some other statements I kind of want to mention. Potential difference. The difference in electric potential between 2 points is called the electric potential difference or voltage. It is the energy difference per unit charge. Again, this per unit charge thing, which is a little bit strange, and I'll get into kind of the way I think about it in just a second. So it is the energy difference per unit charge that is required to move a charge from one point to another. So then they have this V here. Normally you have a delta, so because they're talking about a difference from one point A to another point B. And but ChatGPT, I guess, decided not to use that. And we have the work. So here we have the work done from point A to point B divided by the charge, per unit charge again. And then here they say where VA and VB are potentials at points A and B, and W, A to B, is the work done to move the charge from A to B. Okay, so now that you've kind of had a chance to look at these equations, I'm going to bring back the main equations that we've been talking about. So we have change in potential. You can think about this as the potential at some point B minus the potential at some point A. Or you can think about this as, you know, if you label the points differently, maybe it is point A minus point B. But if you flip the points like this, normally you have a minus sign that comes out of here. So it depends which one is bigger, right? But if you, like, let's say you take 7 minus 3, you would get 4, 5, 6, 7. Yeah, I'm tripping out a little with my elementary math. But if you take 3 minus 7, you would get the same thing with a minus sign in front of it, minus 4. Okay, so same kind of scenario here. Depending on which point you take, depending on if VB is bigger than VA, you would have this scenario, VB bigger than VA, and you would have a positive sign here. But if you flip them, so you take VA minus VB here, you would have this scenario with just a minus sign. If you take the magnitude of this entire difference, you should get the total, magnitude here, where both of these give you 4. So that doesn't matter too much. Just wanted to show you that electric potential is normally looked at as a difference. And before I get into my further discussions, I want to tell you guys why it's looked at as a difference. And one analogy I see a lot is altitude. So I'm going to bring this up here and bring up this analogy, altitude. So let's say you are on a mountain. This is you up here, right? And you've taken some energy and work to climb this mountain. Let's say you get here, and over here is your base camp. So you have like a little fire right here. This is where you started the journey from, your little tent. And the altitude of the mountain from your base camp is a distance, let's say it's like 1,000 meters up. So you can phone your friend and say, yo, I am at an altitude of 1,000 meters above you. But normally when people talk about altitude, they actually refer to it from sea level, because that's kind of a standard sort of position taken to, I guess, standardize altitude for all people. So let's say from sea level to this base camp here is maybe 200 meters. So if you phone another friend, like chilling in a house over here, this guy, you would say, yo, my altitude is actually 1,200 meters from sea level. Or you could literally just say 1,200 meters, and this guy over here should know that you are referring to the reference point as sea level. And that's normally what's happening in discussions of altitude. If you had another friend here that's climbing like this, and his distance is maybe like 100 meters up, then you would call this friend and be like, yo, my altitude is 100 meters from you. So in that case, you're referring from this reference point, not from the base camp reference point and not from the sea level reference point. So in order to avoid this confusion and not to talk about sea level, most of the time altitude is taken as a change in altitude. So you can always phone your friend, maybe this friend here, and say, yo, my altitude difference from you is 100 meters. That's not confusing at all. You can phone this friend and say, yo, my altitude difference from you is 1,000 meters. Again, not confusing at all. You can call some other dude and say, my altitude from sea level is 1,200 meters. Again, not confusing at all. If you had a friend over here in a submarine, and for some reason you had to tell him your altitude, you can tell him the altitude difference from here to here. Maybe it is 2,000 meters, the altitude difference. And again, there would be no confusion. But in the real world, normally we don't really talk to people under submarines when we're talking about altitude. And normally there's very low amount of cities that are actually built below sea level. So most of the time we take sea level as the unit for reference for altitude, and the equation for altitude now becomes your current altitude, current alt, minus the reference altitude. Okay, and if the reference altitude is sea level, and we label sea level as equaling 0 meters, 0 meters from sea level, then this equation here, the altitude, becomes a very simple equation. You can just remove this reference level and say, oh, this is sea level. And if you know your current altitude, then you can just subtract 0 from sea level, and you get a very simple equation. The altitude change is just your current altitude. So you can give this guy a singular number, you can give this guy a singular number, this guy a singular number, and since we've all agreed that this sea level is our point of reference, we all know that, the altitude change is from sea level. And if this person here knows that his altitude change, his current altitude, what that number is from sea level, then he can do some quick math and find this altitude change over here. Same thing with this guy. So in the real world, we normally take this sea level as the reference point, I guess, where we measure heights off of, and we, there's no confusion there. But you can imagine other scenarios where, let's say, for example, we were in a building, this building is on a city and sea level is all the way down here. And you're doing an experiment on the 3rd floor where you had a table and you were doing some kinematics experiment where you're dropping a ball off. You're gonna talk about the change in height just in this scenario. So this would be change in height. Maybe you're gonna run some equations there. You're not gonna talk about sea level here. So that's why this change in altitude is like the final sort of ultimate definition for height or change in height or whatever that you should use. Same thing with potential difference. So in some books they talk about potential at a certain point, so they give you just one number and they don't give you a potential difference like this because they assume that the reference point, so for example this VA, is known. And normally in circuits the reference point is ground. It is written like this. Ground has a potential of 0 volts. So it is kind of the same analogy as sea level here. So I hope that made a little sense. I don't want to talk about that too much. You're going to see how it comes into play when we calculate the potential of a point charge. But I just wanted to give you guys kind of that quick explanation here. And the next thing I kind of wanted to get into was the discussion on this per unit charge thing. So if you remember, we described electric potential or electric potential difference like this, and this was literally defined as change in electric potential energy or work, right? This or work comes from the equation up here. Change in electric potential energy is equal to an opposite to the work done on the system. So change in electric potential energy or work per unit charge. This is defined as electric potential difference. So this little per unit charge, so this is like joules per unit charge. You can think about the units to maybe help you out a little bit. So this is how many joules per unit charge. Normally the unit charge we use is Coulomb. This gives you units of volts. So volts are joules per unit charge. You guys saw that kind of mentioned 3 different times in the Wikipedia articles and the ChatGPT over here. The way I think about this fraction over here is the way a speedometer on a car works. So if you look at a speedometer, you have normally a arrow here pointing to 0, maybe 50, maybe 100. And this, if you were in Canada or anywhere except the States, is going to be in units of kilometers per hour. So how your car actually calculates this is it is driving, right? This is my Lambo. I am driving and the car has a clock inside of it. So this is a little clock, right? And it starts counting how much time is passing over some distance. So let's say I travel 37 kilometers and my clock calculates 37 minutes. Or actually, let's use hours to stay with my analogy. You're driving pretty slow here, but this math will work out pretty nicely. So the car is doing a ratio here. It's saying, what is the distance that I'm traveling per unit time? So it's doing this division here, and the unit time that we are choosing is hours. We could have chosen minutes, but in this case, the unit that we are using is hours for time. So this will give you a speed, a distance per time. So normally in for velocity, in physics classes, we use meters per second, but cars typically use kilometers per hour. So here, 37 divided by 37 is 1, and we have kilometers per hour. So normally you see it like this, 1 kilometer per hour. If let's say we had a different value, so let's say we were going 60 kilometers for every 2 hours, we drive 60 kilometers, my car is giving me a time value over here for the internal clock for 2 hours. We divide 60 by 2 and we get 30, and then we put the units kilometers per hour. So this thing here is the per hour that you keep hearing, except in our case, it is not a velocity, it is a piece of energy per unit charge. So in some scenarios, the battery that you have, it might be moving a lot of charge. It might be moving 30,000 coulombs, or it might be moving 1,000,000 electrons. Electrons have a specific value for charge. It's basically doing this same thing over here. It is finding how much energy it's taking for the potential difference to move a certain amount of coulombs. Let's say it takes, literally the same example as the car. Let's say it takes 60 joules per, it's moving, I don't know, 2 coulombs. This will create a potential difference of 30 joules per coulomb, or we define this new unit as volts. So 30 volts. So I hope that maybe simplifies this per unit charge thing quite a bit. I know it's a bit complicated, but don't worry about it too much. I don't think you're gonna see too many problems with this here. It's just kind of a way of thinking about why this per unit charge comes into play. It's the same thing as a speedometer in a car. You have kilometers per hour. Instead of telling you this value here, 60 kilometers per 2 hours, they just divide out these numbers and they give you just per unit hour. Or if it was minutes, they would divide out the minutes and they would do per unit minute. Okay, so you could think about this the same kind of way. It's kind of the potential difference is a way of calculating how much work or energy it takes to move a certain value of charge, and the value of charge is not always going to be 1 coulomb. It might be 30 coulombs, right? It might be something different like that. So those are my little discussions here, and now we are going to get to my problem for the day. It will be to calculate potential around point charge. Okay, so in the first chapter we learned that we have a positive charge and it shoots out an electric field like this. It is equal and radiates in all radial directions. So here I'm just drawing a cross section. Imagine you had imagine, I guess, you had a spherical point charge. Whoops. I mean, a point charge is just a point, but I'm going to just draw a 3D scenario here to show you what I'm doing. Since I'm drawing on a piece of paper, it's 2D, I need to do a cross section. So imagine I cut this thing in half, and then I rotate a little bit, and I'm just looking directly at the cut slice. So here I have this going in the background, and what I'm looking at here is like the little cut that I made in the center over here. That's what I'm drawing over here. So these electric field lines, these ones going out radially in all directions, you should imagine them coming out in all directions. So some coming out here, some coming out directly at you, some going directly into the page. It's a three-dimensional problem, right? The electric field lines are equal and they radiate in all directions. And in the first chapter of the book, what you learned was that the electric field for a point charge like this, it has a specific value, and that value is written like this. So it is a vector, right? Because these things have a direction. They all point radially outwards. And the magnitude of this electric field is the Coulomb constant, which is always a constant. You can look it up in some book, search it up online. The charge Q, so the charge that is creating the electric field. In this case, it is a point charge. I'm just going to label the charge as lowercase q. Could be anything. It could be the charge of a proton. It could be the charge of a electron, or a positive electron in this case, a positron, whatever. I'm just going to put that charge generally as q. And if you want to find the electric field at some distance r, at a point P over here, so this distance is r, you put that over here and you square it. So what this means over here is that the electric field is inversely proportional to 1 over the square of the distance. So as you get further, let's say this distance was 2, and we double this distance to 4 over here, the electric field would now be 1 over 4 squared as powerful. So it gets much weaker. If you plot a graph like this, and we put the electric field and we put the distance here, it would fall off as a function of 1 over r squared. Similarly, the electric field is proportional, directly proportional to the charge. So the charge here is Q. If I put 2Q, the electric field would be 2 times as strong as when it was 1Q. If I put 3Q, the electric field at this point would be 3 times the electric field if it was 1Q. If I put 57Q, it would be, at this point, 57 times the original electric field as when it was 1Q. Make sense? Now, another thing you might see is, since this is an electric field in a vector form, over here, nothing has vector quantities. It is just numbers. This is a scalar, this is a scalar, this is a scalar. Scalar is another way of saying number. It has no direction, just a magnitude. So where you get the components of the direction are normally in this little bold r following the equation, which normally has a hat. So what is this r hat? This is a unit vector. So if I draw r hat, let's say this is r hat, the unit part of it, unit means that length of this vector equals 1, okay? That is any vector. If I had the vector A, right, and this vector looked like this, let's say it was 37 meters long, right? How I can write this vector is I can do A is equal to 37 meters and multiply it by A with a hat on top of it. And what this A with a hat is the vector pointing in the same direction as the vector A, except instead of a length of 37 meters, it has a length of 1 meter. Make sense? We have a vector here, its length is 1 meter, and we're multiplying it by a scalar, which is 37 meters. All of that together gives us the final vector, which is A, which has a direction, this direction, and a magnitude of 37 meters. The electric field could be thought of in the same way. You have the magnitude, which is all of this stuff over here. Ke, it's a constant. Q, it's also a constant. It is the charge. And r squared is just the distance where you're looking at the electric field for. Multiply all these numbers together, and it gives you a strength of the electric field in these units, newtons per coulomb. But since the electric field is a vector, you need to have a vector component which tells you which direction the electric field is going. And why this is an R is because the electric field is going radially away. Okay, so another thing that is important here is this is radially away from Q. Okay, that's by definition. In other electric fields, for example, the electric field of inside capacitor plates, oppositely charged capacitor plates, this electric field is uniform. Oh, sorry, it is normally going from the positive charge into the negative charge. So this electric field does not have this kind of format because the electric field over here is for a positive point charge. So the electric field will be different in this region here. It would be, well, I don't know what it is, but it's going to have some strength like this, and it's going to have some direction. Let's call it y hat, okay? Because if we create a xy axis here, xy axis, the direction of these guys is going in the negative y direction. So in this case, this E over here would have some negative magnitude, and it would be pointing in the y direction, in the negative y direction. If I had positive, it would be pointing in the positive y direction. If I had a positive electric field going in the x direction, I would have an x hat over here, and that would give me an electric field going like this. So we have a magnitude times a direction, and that gives us the total electric field, the total vector quantity. If you want to learn more about that, I would say search up, you know, just standard vector algebra. If you've never learned vectors before, I would say take a look at that. But the main important thing is, when we calculate the potential around a point charge, we need to know the electric field, and we also need to know the direction of the electric field. So I just wanted to point that out to you guys there. Now let's bring in to play the equation that we're going to use to calculate the electric field. We have the electric potential difference, which will be negative electric field. This is why I wrote the electric field here, because we need the electric field to calculate the potential difference of a point charge. And we have the dot product with a little displacement vector here. And if we want to say, oh, what is the electric potential from some point to another point? We can do, the electric potential difference. Let's do VB minus VA is equal to this. And normally we do the smaller number here as the smaller number on the integral, and the bigger number here as the bigger number on the integral. But like I said before, if you flip these numbers, you just get a minus sign in front of this whole thing and a minus sign in front of this whole thing, which combines with this one to give you a plus sign. So no need to worry about that too much. Let's bring back the original equation. We're going to use this to solve the problem for what is the electric potential around a point charge. Now I'm going to bring in one more thing, which is a picture right here, and you might see from the bottom of this picture, let me put it right here, that this is actually from the Feynman lectures. This is the thing that I introduced in the previous video where I introduced the electric potential, and this is from chapter 4 section 3 of the second book, which is talking about electric potential. So if you want to take a look at that, I would say just search that up there. I'm specifically bringing up this picture here to show you that the electric field is a conservative force field. What does that mean? I'll get to that in just a second. Let me just crop this so I can eliminate some distracting stuff. Okay, so the claim that I'm making is the electric field is a conservative force field. You might not know what this means, and honestly, it's not too important. Well, it is very, very important, but for the purposes of this video, the main word that is important is this conservative. So when a force is conservative in physics, it just means that it does not depend on path taken. Now, what does this mean, and why is this picture important? Well, here you will see the positive point charge Q, which I have drawn right here. And you will see that these lines over here are the electric field lines, similar to the ones that I drew here, except just a little bit more nice. And they've only drawn a few, so these actually go out in all directions, towards you, in the back of the screen, radially in all directions with this magnitude. Over here in part B, you will see the same thing, a positive point charge, Q, with a couple more electric field lines drawn, and there's a path taken between both of these, and the path is different. So the path is going from point A to point B in both scenarios, point A to point B. It's the same path, and is actually the path that we're going to use to calculate the electric potential. So what we want to do is, okay, we start here, and we have, let's say, a point charge. Let's say it is a positive charge. You know that it creates a repulsive force due to Coulomb's law, and you know that there is an electric field created by both of these with this magnitude. Now what we want to do is calculate the potential difference, and what that is by definition is what we saw over here in the couple of definitions. It is the work per unit charge that it takes to move a hypothetical charge inside some electric field. So from the equation here, we have the electric field. The electric field is created by the positive point charge, and we have the path ds. Remember, this came from force equals, work is equal to force times distance. This is the distance that we're going to move, and this is the distance from point A to point B, from point A to point B, from point A to point B, from point A to point B. Make sense? The path that we're taking is different. So you might see or have an inkling or a prediction or a hypothesis as to what the electric potential will be for both these scenarios, scenario A and scenario B, when the path is different. In this case, we start at point A and we go to this point A prime, right? And the direction we're going is radially away. We're following this big circle. If I can draw the circle over here, it is like a circle that is at an equal radius from the point charge, and that radius is radius A over here. So you can see this radius is A. This is the same radius, A, except they call it A prime here because it's a different point, right? We are moving to a different point in space. But it is the same distance from here to here. You could see this, all these lines are the same distance. So what that means is the electric field at this point will be Q over A squared, because A is the radius over here. So what that means is this field here, the electric field is a constant. It is one number. It doesn't change along this path here. And that might lead to, the reason why the electric field is a conservative force field. So this is the path we're taking from A to A prime, kind of along this little circle path here. If you go along all the way across this point charge, you will get back to the same point because you're not moving towards the point charge or away from the point charge. Once we get to point A, we're going to move the hypothetical charge all the way radially away to point B, which is the final point. That is scenario A. In scenario B, we're taking a different path. Notice this path looks like this path looks like this. They are different pathways, but they're starting at the same point and ending at the same point. They just take a different path, right? I could have another scenario here where the pathway I take is some crazy wiggity-woggity path like this, and then I end up at point B there. They're all going to be different pathways. And what we're doing is we want to calculate the potential difference between these points here. So how do we do that? Well, we have the electric field that is created by this positive point charge Q, and we have the path taken. So you could see these paths are a little bit different, and to make it a bit more simple, I'm going to start off with this path here. And what I actually want to do is create the integral that represents this path. What I want to do is find the potential difference between point B and point A, or point A and point B, whatever, it doesn't matter. You can flip these two, and again, you'll spit out a minus sign over there. The final potential difference will be different. And this is the equation we have to work with. The electric field, the starting point, the ending point, and the path taken, ds. Now remember, ds is ds because this is the total path, right? That is ds total, for example. You could call it that. But the reason we have a little ds here is, one, this is a differential displacement. You can take a look at the previous video where I kind of spoke about why we should break things up like this. But the main reason is, if you want to find the work equals force times distance for a object moving along some distance like this and with a constant force like that, you could literally just multiply the numbers together like this. Then I told you guys why the dot product is important, because if you had a force pointing in some other direction, then this angle here between the force and the distance, the dot product will help you find the total work done, because work done in perpendicular directions like this is equal to 0. So work equals 0 there. Now, if you had a more complicated path, it wasn't straight like this, it instead went into some crazy pathway like that, then what you want to do, and why calculus is very important here, calculus, this little differential quantity and this integral, is you break down the path into these tiny components, which we will call ds, and you can actually find the work equals force times distance for each one of these little points from the start all the way to the end. And if you add an integral over here from the start to the end, then you will get the entire work done on this entire path, even though the path looks all weird like this. So that's why calculus is very useful. Don't worry about any crazy integrals. In a kind of starter course like this, you will not have to do any crazy integrals. It's just important to know where this ds comes from and why it's coupled with an integral. Okay, now that all of that is said, we're going to get to the problem. So what I'm going to do is model this path using this integral here. And what I'm going to do is start on a blank page over here, and I'm going to literally write potential difference from point B to point A. I'm writing them like this because I'm assuming that, you know what, I'm not gonna write this, just to not confuse anybody or myself. I'm gonna write it like this, so electric field dot ds. Okay, now let's replace what we already know is true. We have the electric field, right? It is literally the electric field from here. So I can copy that entire thing if I want to, and I will. I will go like this. I'm gonna copy also the unit vector, okay? Remember the unit vector, and you're gonna see very soon why I decided to explain all of this stuff here. Because, patience. If you remember, what's going on in this integral is here we have a vector, vector A, for example, that is the electric field, and we have the dot product with this vector, ds. I forgot to write a little vector quantity here. This is a dot product. The dot product must take two vectors in. And if you did not have this, then this thing is not a vector, and the dot product with the ds here would not work. So you need to have this r hat, because r hat, yes, I know it has a hat, and it is a unit vector, but it is still a vector. That is the important thing. That's why the dot product will work here. If you did not have this and you only had these scalars, the scalar does not fit into the dot product. So I'm going to complete the integral over here. We have ds, which is the dot product, and that is the first step of simplifying this integral. All I did was plug in my electric field. And keep in mind, if you have the dot product, you must have two vectors in play. So what do we do here? Well, take a look at this. This integral is going from point A to point B. And in our case here, in the case that I drew here, which I took from the Feynman lectures, we are actually breaking down this path from point A to point B. It's not going directly from point A to point B. It's taking this intermediary step at point A prime, and then it's going to point B. So let's actually break down our integral using that fact, right? And how you break that down is, well, you put a minus sign here. Actually, before we do that, we can simplify the integral a little bit more. Take a look at this. Ke over here is a constant, right? It does not depend on the position. It is literally just a constant. And so is Q. This is a constant. R is not a constant. And why is that the case? Because R is the position from the point charge Q, where the electric field is being calculated. And also R is connected to this R, which is attached to this dot product. So this dot product, we have no idea what's happening in here. This is a confusing mess. This is not a constant. We can't pull it out. Ke, for sure, 100% a constant. Q, for sure, 100% a constant. R is not a constant. And you can just see this from here. This, for example, is distance RA, right? You can say this is length A, or you can say this is R subscript A. You can say this is RA prime, for example. But it is literally RA prime is equal to RA. But once we go from here all the way to here, then we are changing R. Here, R is equal to A, and then over here, R is equal to B, and these two are not equal. So R is not a constant. So all of that mumbling was to basically tell you guys that we can pull out Ke and we can pull out Q from the integral, okay? And now back to the original point. I'm going to put a big bracket here, and I'm going to break apart the first integral, which goes from A to A prime. One thing that I didn't really mention is that the electric potential, written like this, is actually a, what is it called? It is a line integral. So this integral is over ds. It's a very strange integral. It's not the classic integral dx. This is the first type of integral you see in calculus class. It is actually called a line integral. And that is because it is going over this pathway here. So instead of having a classic function like this, where y is a function of x, and then here we have, for example, a, and here we have, for example, b, and you're integrating over the x-axis, and you find the area over here. This is a classic integral. What you're actually doing here is integrating from this point all the way here and then all the way here. It's a line integral. In this case, you're going over this line. So it's a slightly more complicated integral. You won't really have to look at this until you get into like calculus 3, for example. And that's kind of why a course like this is a bit more complicated, because it is dealing with these advanced calculus topics that you don't really learn about until a bit later on. But basically what I can do with that is decompose this integral, this line integral, into its two different sections. And since I'm modeling this example here, I'm going from this point to this point, I will break apart this into one integral and then this into another integral. And if I add them up, I should get the total final integral. So if you haven't seen that before, no worries, just take a look at how I'm doing it here. Remember, we pulled out this KEQ as constants. So now I'm just going to recopy what I have in the middle. So I have r squared, I have this dot product with the r hat vector and the ds vector, and that's it. Now I'm here, I'm going to put a plus sign. Here now I'm starting my path integral from a prime, right? A prime, and I'm ending off at b. And I have the same thing, right? I'm integrating over the same thing. Here I have r hat dot product ds, and I can close these bounds. So this entire thing is equivalent to the first integral I have. I just pulled out some constants, and then I'm going, from here all the way to a prime, and then here I'm going from a prime all the way to b. So I'm taking this middle step, this a prime middle step, but my starting point is still a, and my final ending point is still b. And I have all this stuff here that I haven't worked out yet. So what are these things in the middle? Let's take a look at them, and let's take a look at them one at a time. Remember what the dot product was actually telling you. The dot product was actually telling you that you can, well, if you remember this dot product identity, you know that you can take the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. Okay? This you could literally plug into here and you should be correct. But what I'm going to do is I'm going to go back to our picture, and I want you guys to take a look at what this vector is and what this vector is and what the angle between them is. So, and also keep in mind that I split up the integral now. So I'm first going to look at this section, and then later I'm going to look at this section. In the first section, I'm looking at this pathway here. So if this is the pathway, this is ds, okay? This is the direction of ds. But the r hat vector is pointing along these directions. So this is the r hat. And the reason is because r hat is literally describing the electric field. And these lines here are the electric field lines coming from the point charge Q. So I'm going to draw that over here very, very lightly. So over here we have r hat. Over here we have r hat. And in every path in the middle we have r hat. Meanwhile, from A to A prime, we are passing this blue line, which is ds. So if you take a look over here, the angle on all of these is actually 90 degrees in every scenario. So the angle between these two guys is 90 degrees. And if you remember, cosine of 90 degrees, if you plug this into your calculator, is 0. So technically what this is saying is the potential from point A, the potential difference, I guess you could say, potential difference from point A to point A prime is equal to 0. There is no potential change along this pathway here. It's almost like saying there's no work done moving the particle from here to here. And why is that the case? Because the electric field is a constant along this line, along this specific line over here, this specific line right here. That is because the magnitude of the electric field is always at this, sorry, I shouldn't have drawn a vector there. It's always at this radius A, here and here. So that means the magnitude of the electric field is constant. And also, the angle between these vectors will give you a 90 degrees, and the cosine inside of the dot product will give you a 0. So all of that said, if you go down to here, you can expand this entire thing as, magnitude of r hat, magnitude of ds, and then multiplying by 0 here. So this entire thing is equal to 0. That means this entire integral here you can replace the inside by 0, and if you have an integral something 0 ds or dx, for example, this entire integral will equal 0. So I will leave that there for a second, but what I'm going to do is just copy down the answer to the integral. So I'm going to copy down minus KEQ. I have a big bracket, and I'm going to do literally 0 plus. And now I'm going to move on to calculating this guy here. Is that okay? Again, keep in mind what r hat is. Whoops. Keep in mind what r hat is, what ds is, the angle between them in the specific path that you're moving, and you'll see that you actually get a cosine of 0. And that's very interesting. And you can also see that same thing happening from here to here, and also along all of these tiny pathways here. So now let's go and see what the dot product or the entire path integral along this path ds will be. Let's move down here, and again we have the same integral, so the integrand, the thing inside the middle of the integral, is the same, but the pathway is different. Now we're going from a prime to b, which is going along a different path. From a to a prime, we were moving along a constant electric field. We were moving, I guess you could say, along this perpendicular radial path. But now we are moving, in fact, completely radially away from the point charge. So from point A prime to B, the electric field will actually change. It's going to change from a magnitude E is equal to KEQ over A prime squared. And it's going to go to a magnitude here, E is equal to KEQ B squared, if this entire distance was B. So let's draw the same thing that we did down here, because expanding this dot product and this dot product, it's going to look the same way. You're going to have magnitude here, cosine of the angle between them, except you're not going to have this section over here. So I'm going to erase that. And why you're not going to have the same section is because cosine of these two vectors, r hat and ds, is now going to be different. Let's take a look at what r hat and ds look like for this pathway. Remember that the r hat vector points radially away, r hat, and it has a length of 1. And in this case, the ds is the path that we are taking here from A to B. So this is ds. And if you take a look at these guys, the angle between these guys is 0 degrees. And if we take cosine of 0 degrees, what we get for here is 1. Okay? Now let's go back and quickly write that in before we forget. So we have r hat, magnitude of r hat. I'm going to fill that in just a second, magnitude of ds, and we have cosine of 0 degrees, which gives me 1. Okay. Now, what is r hat? What is the magnitude of r hat? Well, I told you guys all the way in the beginning, this is a unit vector. Anything with a hat on top of it has length 1. Has length 1. That is r hat. Okay, so we can literally replace this with a 1. And then here we have ds, and then here we have 1. So it looks like this entire dot product just gives me magnitude of ds. And it's, you know, you can replace that here. So what we solved was basically all of this is equal to ds, and you can remove this entire thing and replace it with ds, and it should be okay. In the first integral, this entire thing, it equaled 0, so we replaced that there. In this case, we got a different value, ds. And you could replace that, but take a look at what's left in the integrand. It is this thing r squared with 1 over r squared there. So let me just remove all of this stuff that I drew here. What you actually want to do is take a look at what ds is. ds is the pathway going along, let me erase this stuff here too. So ds is the path going from A to B here. It is going in the same direction as r hat, except it's going a distance of, for example, from A prime all the way to B prime here. Or, sorry, not B prime, but just B. This, you can actually change it from ds into dr. And why is that the case? Because it's moving in the completely radial direction. So this ds is a arbitrary explanation of the path taken. This is the end point, this is the start point, and these DS's were breaking down the whole pathway here. In this case, we're going along a straight path, and we're going along the direction of r hat. So you could just say this is ds. You can also say another thing. If you don't really like what I was saying there, you can say that r hat dot ds is like, I'm going to write it out here in red. This thing is like the projection of r hat onto ds. And what that literally is equal to dr. So this projection, you can take a look at dot product projection. Literally just search that up online and see what you read. It's another way of looking at the dot product. The way I explained it normally is with this identity here, but there's another couple ways of looking at the dot product. That gets more into a math class. In this case, we just want to take math and use it to solve physics problems. So I'm not going to really get into, I'm not going to get further into the projection way of looking at the dot product, but it's a very interesting thing. I might do a video about it later. For now, just know that you can expand this ds into a dr. And why that's useful is because, well, all we have left here is something r squared. So we don't want to have the variable be replaced with this ds, because then we want to change, we don't have the proper variables to solve the integral. We have 1 over r squared and ds. It's like having integral y dx. You can't solve that. You have to have something x dx, like this, or something x squared dx, right? You want to have the same variables inside the integral. But what's cool is, what I wanted to show you is this entire integral goes to 0, while this entire integral does not go to 0. It goes to something else. So now I'm going to finish what I had here, and in order to do that, I'm going to just take this and slide it down a little bit. So what we have left is, again, I'm going to copy down the exact same stuff we have. We have the integral from a prime to b. We are going to recopy this r squared because it didn't change into anything. And then again, I said ds here, you can change ds because ds used to be a vector. Whoops. Right here, it was a vector. Over here, we took the magnitude, magnitude, magnitude. Here, we left off with ds. And I'm telling you, ds is going in the same direction as r, dr. So you can replace this whole thing with a dr. Hope that is, you know, sitting fairly comfortable with you guys. But take a look at this integral. You guys can solve this integral, I'm sure of it. First of all, we can remove this 0, we can remove this plus, we can remove this, and we can just replace this whole integral with what we have here. Now take a look at what happened. We started off with the original equation like this. We simplified it by plugging in, well, we didn't simplify it, we actually made it look like our problem by plugging in the electric field. Then I split apart the integral into 2 different things because what I was looking at is 2 different pathways. Depending on my path, I could have split up the integral into a bunch of integrals like this. But I want to do it a bit more simply. I'm going to choose this path here. And then I'll show you how this path and this path are equal. You might already kind of see where I'm leading at with this, but after that, I wanted to simplify each of these integrals in order to solve them. So I asked myself, what do I simplify here? This is 1 over r squared. I can't do anything with that. This is the dot product. It looks a little bit scary, but expanding it with the dot product, we can break it down into a couple steps like this. We saw that one of these integrals equals 0. We saw another one of these integrals simplify, so this whole dot product, you can replace it with a dr. That's not going to be the case all the time. Maybe there's some other problems where it's a little bit different, but don't worry about it. At the final stage, we get to this, okay? Now, let's solve the integral. We looking good. So what this integral looks like is literally an integral of r to the minus 2 dr, okay? And how you can solve this is, well, with integrals, what you do is you add 1 to the exponent, so this becomes plus 1, and then you divide by the exponent that you see, and this is a plus c. So r to the minus 1 on the bottom, and the denominator, sorry. And what we have here is the same constants that we saw at the front. I'm going to put big square brackets, which is how you solve integrals. I'm going to replace it with, I'm going to put the minus 1 on top, because minus 1 in the denominator, minus 1 in the numerator, it's the same thing. And then r to the minus 1 is just r in the denominator. I'm not going to put the plus c because we are doing a definite integral, and the bounds of my definite integral are this over here. So, cool. Now let's solve this. We have minus here, we have KEQ, and how you solve this is you plug in the top bound. So I have minus 1, I plug in the top bound into r, which is b. I put a minus sign, and then I put the same thing over here. The bottom bound, which is a prime, okay? And now I can get an answer over here. I can kind of simplify this a little bit by taking this minus sign and foiling it over into here, just because I want to get rid of the minus sign in front of the equation. So you can do that. You don't have to do that. It's up to you. What that looks like is this minus 1 over here on top of the b turns into a plus 1. I have, well, this minus combines with this minus to give me a plus, but then this minus comes in to turn the full thing into a minus. So I can do minus 1 over a prime. Okay? Now, keep in mind, our original integral was integral from a to b, yada yada, random stuff inside, right? Look at the top of the page. We have integral from a to b, integral from a to b. This is the stage where I broke it down with the arbitrary step in the middle. And I found out that this whole integral was 0. So technically, my answer here is the same as my original integral here, which is going from the initial point to the final point. So what I can say is, instead of having this a prime here, I could just replace this with an a, and it's literally equal to my original integral. This is kind of another way of saying that the pathway taken over here equaled 0, because it is the same as going from here to here. So I guess you could say this is a proof of the electric field being a conservative force, because conservative means that the path taken does not matter. So what that means is the electric potential will be the same going from here to here in any pathway. In this example, I chose this pathway, and I found out that the line integral along this section here equaled 0, and only the line integral here mattered. If you take a look at part B over here, you will see the same logic could be applied here as all of these tiny points here. So the, I guess, r hat and ds, these are perpendicular. So cosine of 90 degrees at all of these stages will give you an integral of 0. That means all I need to do is add up the integrals from here to here. So add up all of these guys, and you will see this is literally equal to this whole integral here. And another thing, remember how I said the path taken does not matter, so I can go from here to here exactly like this, or I can take this L path, or I can take this broken down path like this, or I can take any crazy path that I want. As long as I end up right here, the potential difference will be equal. The reason that is the case is because all of these paths, they equate 0, and all of these paths, they add to the potential difference. But if I go, for example, up here, so let's say I start this path, I go to the side, I go up here, I go to the side, and then I go an equal amount downwards, this path here will exactly be the negative amount of this path here, which is the positive. So any kind of pathway taken like this will cancel out any pathway like this. That means if I start here and I go all the way up, go here, and then all the way down, the potential difference is going to be the same as this. It is path independent. It is a statement that says the electric field is a conservative force field. So I don't want to repeat this so much. This video is already very long, but basically the potential difference between any 2 points like this is going to be the same no matter the path taken of the charge. Okay, you can go along this crazy path, you can go to infinity, you can go back. As long as you end up here, if you ask someone what is the potential difference between here and here, this entire path taken, it's not included in the calculation. All it cares about is the endpoints. All it cares about is the endpoints. The potential difference only depends on the endpoints. How you calculate it is, will you take into consideration the displacement and the electric field. But since the electric field is conservative, it doesn't depend on the displacement taken, then this entire integral will give you the same final answer. So I hope that makes sense. Now let's get back here and take a look at this. What these values, A and B, are actually radial distances. So you can replace this with a bit more of a suggestive kind of symbolism, and I can say this is the distance RB, and this is the distance RA, okay? This is the distance here, RA, and this is the distance here, RB, okay? So this is the potential difference between those 2 points. Now, please remember what I said to you guys about, oh, maybe I erased that, but what I said to you guys about that altitude difference. This is like saying, yo, I am at an altitude RB, and I'm measuring from a point RA. Now, imagine we took RA to be at a distance R is equal to infinity. This is what we were saying over here. Okay, here we go. Typically, the reference point is Earth. So Earth is in circuits when you have this thing called ground. Ground has a potential equal to 0, or a point at infinity. So R is equal to infinity typically leads to a potential difference, or sorry, a potential equal to 0, unless in a specific case where the electric field extends to infinity. So remember the point charge? The point charge which was down here? The electric field of the point charge looks like this. It is inversely proportional to the distance. So if we want to take a limit as R goes to infinity, this is another kind of quantity that you see in calculus of the electric field of a point charge. This goes to 0. Why? Because you plug infinity inside of this and you get 1 over infinity. And if you plug this in your calculator, well, first of all, there's no infinity. But if you plug in a super big number like a billion and divide it by 1, you'll see you'll get a super small number like this. So we basically say the limit as R goes to infinity leads to an electric field that is equal to 0. So if we want to take a reference point, this is our reference point. Let's say RA is at infinity. So what this is saying is this picture here, instead of calculating the potential difference between here and here, we're calculating the potential difference between here and this distance if we send this all the way out to infinity. So what does that look like? Well, we can erase all this stuff to make it a bit more simple. Basically, this thing here is equal to 1 over infinity, which is equal to, it goes to 0. So what we can say there is this entire thing in the back half disappears, and we get this simplified integral. And what this is, you can simplify it as KE, Q on the top, over R. This is typically considered the potential of a point charge, considering the reference point is taken at infinity. If you did not want to do that, considering the reference point is taken at infinity, just remember that this is the original equation. But even this, what you have is 1 over R, a distance, 1 over a certain radial distance, minus 1 over a certain radial distance. This will give you 1 over a certain total radial distance. So this is the whole final equation of the electric potential of a point charge anyway. So I hope that made sense. Please just consider that when you're sitting in a test, they're going to tell you, okay, we have a point charge and the potential. They're not going to say potential difference. They're just going to say potential now because we are considering that the reference frame, or sorry, the reference point is at infinity. So this entire thing goes to 0. So they just take this component here. The potential of a point charge is literally KE Q over R, which looks very similar to the electric field. The electric field had a square over here. The potential doesn't. So this is something they're just going to give you. But how you calculate it is you go through this kind of integral breakdown thing. And again, if you want to find the potential difference due to any electric field setup, you just go through this kind of solving process here. So I hope that was helpful. I know these videos are long as shit, guys. Thank you very much for watching. I appreciate y'all. And yeah, peace.